Hi, everybody. In this little video, we're going to talk about percent compositions and calculating empirical and molecular formulas. I know it's kind of odd that you can only see me writing. Hopefully next week I'll have some better technology where we can videotape me talking and writing at the same time. That would be more familiar to you that our lectures would have been like. But this is the best I can do for this week. So percent compositions. Percent compositions are similar to any other percent calculation. In general, remember a percent is equal to a part divided by a whole times 100. So in percent compositions, sometimes called mass percents, what you do is you put the mass of a particular element, I'm just going to call it element A, and you divide it by the mass of the compound, multiplied by 100. So these masses could either be for individual molecules or formula units, in which case the masses would be in AMUs, atomic mass units, or what I like to use is moles of molecules, and then it's the mass of a mole of the element, and so everything will be in grams. I just myself find it easier to write gram than AMU as we're going through the calculation, but you could do it in either, you'd get the same answer. So let me show you what I'm talking about with an example. Say that I asked you in the formula C2H6O to calculate the percent carbon. To do this, what we need to do is get the mass of 1 mole of the entire compound, and we've already calculated molar masses several times, so hopefully you know how to do this using the periodic table in the formula. Our formula shows we have 2 carbons. The periodic table tells us the atomic mass of a carbon is 12. I'm going to stick with moles, so I'm going to end up having grams, but that's going to give me 24.0 grams. In the formula, we have 6 hydrogens. Hydrogens are 1.0. That's going to give me 6.0. Whoops, it's a little sloppy. We have 1 oxygen, and oxygen is 16.0, so that's going to give us 16.0. And if you add 24, 6, and 16, you're going to get 46.0 grams. 1 mole of C2H6O would have a mass of 46.0 grams. So if I want to find my percent carbon, I take my mass that is just carbon, which is the 24.0 grams. This is the mass of carbon. And I'm going to divide it by the mass of the entire compound, which is 46.0 grams, and then multiply it by 100 to get it to percents. And 24 divided by 46 is to 3 sig figs, 52.2%. If I wanted to figure out my percentage of oxygen, the only difference I would make is my numerator would not be 24, but my mass of oxygen would be 16. And I'd go 16 grams divided by, by 46.0 grams times 100. And 16 divided by 46 times 100, I believe comes out to be 34.8%. So this is a fairly easy calculation to do once you know how to do molar masses. So I'm going to try one more. You can put me on pause and you can try to do the work and see if you get the same answer as me. So calculate the percent nitrogen in formula NH4CO3. NH4CO3, NH4 is ammonium, CO3 is carbonate, so this compound would be ammonium carbonate. Just to practice some naming. So if you want to pause and try it and then see if you get the same answer, that's a great idea. If you want to just follow along, you can, but make sure you know how to do this. So in our formula, how many nitrogens do we have? 2. Remember, this 2 is going to go, this 2 is multiplied by everything within the brackets. So we have 2 nitrogens, having trouble writing today. So I'm going to have 2 times 14.0. And I have 8 hydrogens. So I'm going to have 8 times 1.0. Again, remember I'm getting these numbers, the 14 and the 1, from the periodic table. We have 1 carbon. Carbon is 12. We have 3 oxygens. Oxygen is 16. Adding that all up, I'm going to end up with 96.0. It just turns out that these all were at 0.0s. That's just a coincidence. I didn't mean to pick them all to be 0.0s. It just turned out randomly. That's what I chose. So again, if we're doing this with the units of grams, we would have all of that, all of the G's added in. So the percent nitrogen is going to be the mass that is just nitrogen right here at 28.0 grams divided by the mass of our entire compound, which is 96 grams times 100%. And if you did your calculation correctly, hopefully you got 29.2% nitrogen for that compound. So I don't think these calculations are really too tricky to do. I assigned some in the homework. You can do a couple more for practice. What are we going to do with them once we can calculate them? What we really want to work on is determining for formulas an empirical formula. An empirical formula, sorry, I'm being very messy. An empirical formula is going to be defined as the smallest whole number ratio of elements in a compound. Now there's 2 parts of this. It's the smallest and it has to be whole number. So some examples I could show you is, say the first formula we started out working on, C2H6O. What are the ratio of the elements in there? Well, carbon is 2, hydrogen is 6, and oxygen is 1. Once one of them is already at 1, you can't have a smaller whole number than 1. So this is already an empirical formula. However, if I showed you the formula C3H6O3, that would not be an empirical formula because 3 to 6 to 3 can be reduced. You could divide each of these numbers by 3 and end up with 1 to 2 to 1. This would be the empirical formula, C1H2O1. So the empirical formula is the lowest whole number ratio. So in the next examples, what we're going to do is I'm going to tell you the mass percents of compounds, and we're going to calculate empirical formulas from that information. So here's our first example. Calculate the empirical formula for a compound that is 75.0% carbon and 25.0% hydrogen. So whenever we're going to do these types of calculations, one of the first things you need to do is get from percent somehow to masses. The easiest way to do that, in my opinion, is to just make an assumption that you have 100 grams of the compound. Assume you have 100 grams of the compound. If you have 100 grams of the compound, then that would tell me if it's 75% carbon, that I then have 75 grams of carbon. And if it's 25% hydrogen, I then have 25 grams of hydrogen. So the first step, 1, assume you have 100 grams of the compound. Second step is convert grams to moles. We need to use a molar mass to do this, but since they're always just going to be atoms, you can use the periodic table pretty quickly. And you could say that 1 mole of carbon is 12.0 grams of carbon from the periodic table. 75 divided by 12 is going to be equal to 6.25 moles of carbon. For hydrogen, 1 mole of hydrogen is going to be 1.0. I'm going to stick with 3 sig figs, so I'm going to say 1.01 grams, and that's going to give me 24.8 moles of hydrogen. Now we could try to just stick with the mole ratio, which if we divided them each by 6.02 times 10 to the 23rd to get to individual atoms, we really wouldn't change the ratio. So if you multiply everything by the same term, the ratio is unchanged. So now we really do have the ratio already. It is going to be 6.25 to 24.8. This is the ratio. but an empirical formula is the lowest whole number ratio. So I need to convert 6.25 to 24.8 into a lowest whole number ratio. How do I do that? Third step, divide all by the smallest value. So I'm going to divide 6.25 by 6.25, and I'm going to divide 24.8 by 6.25. 6.25 divided by 6.25 is 1, and 24.8 divided by 6.25 turns out to be 4. So my lowest whole number ratio is 1 to 4. That is the same actual ratio of 6.25 to 24.8. So my empirical formula is going to be C1H4. To show you another example that has a little bit more involved in it, what if I asked you to find the empirical formula for a compound that had the percent composition of 48.6% carbon, 8.11% hydrogen, and 43.2% oxygen? Now this is a compound that contains 3 different elements. You do the same thing, you just have to do it for each of the elements. Step 1, assume you have 100 grams. If you have 100 grams, then I'm going to have 48.6 grams of carbon. I'm going to have 8.11 grams of hydrogen, and I'm going to have 43.2 grams of oxygen. Step number 2, convert them each into moles. 1 mole of carbon is 12.0 grams. 1 mole of hydrogen is 1.01 grams. And for oxygen, 1 mole of oxygen is 16.0 grams of oxygen. Cranking that all out, 48.6 divided by 12 is 4.05. 8.11 divided by 1.0 is 8.03. And 43.2 divided by 16 turns out to be 2.70. Again, these numbers now, 4.05, 8.03, and 2.70 is my actual ratio. But I don't want the actual ratio in that terms. I want them in the lowest whole number. So I'm going to take 4.05 to 8.03 to 2.70, and I want to get it to the lowest ratio. So I'm going to divide them all by the smallest one. 2.70 divided by 2.70 is 1. 8.03 divided by 2.70 is 3.03. And 4.05 divided by 2.7 turns out to be 1.5. Now we have a problem. This is not a whole number ratio. It is the lowest ratio, but not whole number. So how do we get it to a whole number? Well, if it's a half, to get a half to a whole number, I'm going to multiply each one of these by 2. And then my lowest whole number ratio is going to be 1.5 times 2 or 3. 3 times 2 is 6. 1 times 2 is 2. So my formula is going to be C3H6O2. This last step is a little tricky. Some people run into trouble with rounding. If you end up getting something like 1.02, don't round that. You can just round that to 1. You wouldn't want to multiply that by some crazy number to get that up to 2. So look for things that are easy fractions, a half, 0.5, or a third, 0.33. You'd have to multiply that everything out by 3. So try a few of the problems in the book and see how you do on the numbers. And we can come back to this again if people are having trouble. The last part of this is talking about molecular formulas. Now, one thing you need to know is molecular formulas only exist for covalent compounds. There is no such thing as a molecular formula for an ionic compound. Ionic compounds always exist as their empirical formula. They only exist in their empirical formula. So what exactly is a molecular formula then? Molecular formula, I'm just going to call it MF, is equal to the empirical formula times some number n. N must be a whole number. N could be 1, 2, 3, etc. So how do you find that? You find the value n by taking the mass, or I can say the molar mass, of the molecular formula, and you divide it by the molar mass of the empirical formula. And you'll get the value of an n. So let me show you some examples. This is not really as difficult as this may sound. So here's two examples. Before we found an empirical formula as CH4, if I told you that the molecular formula had a mass of 16 grams, then what is the molecular formula? Determine the molecular formula. You need to find the mass of the empirical formula. Well, it turns out that the mass of the empirical formula, 1 times 12 for carbon, 4 times 1 for oxygen, is 16. But 16 is the same as what I told you was the formula, the molecular formula mass. So 16.0 divided by 16.0 is going to give you 1. And it turns out for this formula, CH4 is the empirical formula, but it is also the molecular formula because N is equal to 1. That happens for several compounds, so it's not uncommon that the empirical formula and the molecular formula turn out to be the same thing. Here's one where that's not true. If I told you that an empirical formula was CH, and the compound had a molar mass of 78.0 grams. Oops, sorry, my pen's starting to go crazy. 78.0 grams. Determine the molecular formula. Well, you need the mass of the empirical formula. The empirical formula has in it 1 carbon, 1 times 12, and it has 1 hydrogen, 1 times 1, for a total of 13. But my molar mass is up here at 78. So I'm going to take 78 grams and divide it by 13 grams. 78 divided by 13 turns out to be 6. So that tells me that my molecular formula is equal to my empirical formula times 6. So it's going to be CH times 6, or it's going to be C6H6. Notice this is not a lowest whole number ratio, but the ratio C1H1 is maintained. 6 to 6 really is the same ratio of 1 to 1. So again, there's some problems that I have calculated for you, that asked you to calculate in the homework. We could try to do one more together if you'd like to try. Again, if you want to put me on pause, that would be great, and then you could go ahead and do it. So here's a problem similar to what's in the text for you. 1.45 grams of phosphorus burns in oxygen or in air and creates a phosphorus oxide with a mass of 2.57 grams. The question is to find the empirical formula for this compound. If you're going to do this, you don't have to assume 100 grams in here because it's not really telling you the percentages, it's actually telling you the grams. Notice that in this compound, if it's phosphorus oxide, it contains 2 elements, phosphorus and oxygen. If you know the entire oxide, the compound, oops, let's just write compound. If you know that the compound has a mass of 2.57 grams, and you know that the phosphorus was 1.45 grams, then you can subtract that out. And if you subtract that out, you get 1.12 grams, and this much must be the mass of oxygen. So this one's a little bit different in finding the empirical formula in that I'm not giving you percentages to start with. They're actually giving you the masses. So to start with, you have 1.45 grams of phosphorus and you have 1.12 grams of oxygen. You then proceed the problem and do it exactly the same way. So you would say that 1 mole of phosphorus, using the periodic table, 31 grams of phosphorus, and you would say 1 mole of oxygen is 16 grams of oxygen. And calculating that out, this one gives me 0.0468 moles of phosphorus, and 1.12 divided by 16 is 0.073 sig figs moles of oxygen. Seems my pen has stopped working, so I'm just going to stop. I'll pick this up on the next one, or I'll send you an email with this problem finishing it. I don't know. I think my battery must have died. Hope you have a good one and stay safe.
No. No.
Hold on a minute. This is not going well. First, I hit something that fucked up my whole computer. Now my computer froze and I'm stuck in the middle of the meeting and it won't, I'm like, was at the very end of a 25-minute thing and it froze. I don't know what the fuck to do with this. I hope that's not being recorded for my class. It won't even turn off. My computer won't even turn off.
Hold down whenever you try to hold the button down.
I'm holding it down. Completely frozen. It was the last problem out of like a 30-minute
Oh
session.
my God. Oh,
It won't
all
even,
the other ones done, at least.
huh?
At least all the other ones are
No,
done.
it was, I had one more to go after this one,
Well, that's the
but
last
now
one.
the whole thing is if this is frozen, I can't record anything anymore. That was my second peek of that, because halfway through the first one, I hit Cortana. And I couldn't get her to shut the fuck up in the middle of my
Can't
meeting.
hit your tongue. You should, you can actually type the tongue.
How is it that you can't shut a computer off? Am I missing something here, Petey?
I was gonna look, but I didn't get the feeling.
No, you could take a look and see what you could do. I thought maybe the battery went dead, so I put the charger on it. But this is the on-off button right there. Let's just-
Can I unplug it?
You can do whatever you want.